Here's something that might completely mess with how you think about time. When you look up at the night sky, you're not just seeing stars, you're watching the past unfold in real time. But now, the James Webb Space Telescope has gone deeper than ever before, capturing light from objects that existed just over 100 million years after the Big Bang. Basically, the universe as a newborn. And here's the problem. Those galaxies don't look young at all. So how did the universe grow up this fast? Or did we misunderstand the story entirely? The biggest shock from recent JWST observations is simple to describe, but incredibly hard to explain. The earliest galaxies look far too advanced for their age. According to the standard timeline built around the Big Bang theory, the first few 100 million years of the universe should have been a messy, chaotic period. Matter was just beginning to clump together, stars were forming for the first time, and galaxies should have been small, faint, and irregular. But that's not what JWST is seeing. Instead, astronomers are detecting galaxies that already appear massive, bright, and surprisingly structured. Some of these objects seem to contain large populations of stars and show signs of organization that should take far longer to develop. One notable example includes galaxy candidates like F2000DB-045, estimated to exist just around 168 million years after the Big Bang. That's extremely early in cosmic history, far earlier than our models suggest galaxies like this should exist. So how are scientists even able to see something that old? The answer comes down to how JWST observes the universe. Unlike earlier telescopes, JWST is optimized for infrared light. As the universe expands, light from distant objects stretches into longer wavelengths, a process known as redshift. By detecting this stretched light, JWST can identify extremely distant galaxies and estimate how far back in time they existed. The deeper it looks, the further back it goes. But identifying these galaxies is only part of the story. Scientists then analyze the brightness, color, and spectral signatures of the light to estimate properties like mass, star formation rates, and age. And this is where the tension begins. The data suggests these galaxies are not just present early, they're already mature. That creates a direct conflict with the lambda CDM model, which predicts a gradual buildup of structure over time. In that model, galaxies grow step by step. Small clouds of gas form stars, merge with other systems, and slowly evolve into larger structures. But JWST's findings suggest that, at least in some cases, that slow process may not apply. Now, there are attempts to explain this without breaking the model entirely. Some researchers suggest that these galaxies might only appear massive due to unusual star populations or dust effects that make them brighter than expected. Others argue that early star formation may have been far more efficient under the conditions of the young universe. But even with those explanations, the gap remains significant. These galaxies still seem too evolved for their age. And that leads to a much deeper question. Are we seeing something unusual? Or are we seeing something fundamental that we've been missing all along? To understand why this problem is so difficult, we need to step back and consider something even more fundamental. We don't actually see the entire universe. Everything we observe exists within what's known as the observable universe, a region defined by how far light has been able to travel since the beginning of cosmic expansion. Beyond that boundary, there may be more galaxies, more structure, and more history, but we can't access it. And because the universe is expanding, some regions are moving away from us so quickly that their light will never reach us at all. This creates a kind of cosmic horizon, often described by the Hubble sphere, where the expansion of space itself limits what we can ever observe. This matters more than it might seem, because everything we know about the universe, every model, every timeline, every theory, is built on observations within this limited region. We are effectively trying to understand the entire cosmos while only seeing a fraction of it. Now, JWST is pushing right up against those limits. It's detecting galaxies at extreme distances, close to the edge of what's observable. These objects are not just far away, They represent some of the earliest accessible moments in cosmic history. But interpreting what we're seeing at those distances is incredibly complex. When astronomers estimate the properties of these galaxies, they rely on models of how stars emit light, how galaxies evolve, and how different elements behave under early universe conditions. If any of those assumptions are slightly off, the conclusions can shift dramatically. A galaxy that appears massive might actually be less so if its stars are different from what we expect. Or it might truly be massive, which would force us to rethink how quickly structure can form. At the same time, these galaxy observations aren't happening in isolation. Other discoveries are adding to the puzzle. For example, astronomers have detected evidence of black hole mergers occurring just 700 million years after the Big Bang. That suggests that massive black holes were already forming and interacting far earlier than expected, something that also challenges current growth models. So now we're dealing with multiple lines of evidence pointing in the same direction. The early universe may have evolved faster or differently than we thought. And when you combine that with the fact that we're observing only a limited portion of reality, a new possibility emerges. What if the issue isn't just with the objects we're seeing, but with the framework we're using to interpret them? Because if our view of the universe is incomplete, then our understanding of its history might be incomplete too. When observations stop matching predictions, science doesn't collapse, it adapts. And that's exactly what's happening now. The tension between JWST's discoveries and existing models is pushing researchers to explore new ideas about how the universe works. One of the more grounded explanations is that galaxy formation in the early universe was simply more efficient than we previously believed. Under this view, conditions shortly after the Big Bang, such as higher densities of gas and stronger gravitational interactions, may have allowed stars to form rapidly and galaxies to grow at accelerated rates. This would mean the basic framework of the Big Bang theory still holds, but the details of early evolution need to be adjusted. Another area of focus is dark matter. Although we can't see it directly, dark matter plays a critical role in shaping the universe's structure. If its properties are slightly different from current assumptions, it could significantly change how quickly matter clumps together. That, in turn, could explain the rapid formation of massive galaxies and early black holes. But beyond these adjustments, more radical ideas are also being discussed. Some scientists are exploring whether the universe could be older than the widely accepted age of 13.8 billion years. Others are considering whether the Big Bang was not the absolute beginning, but rather a transition from a previous state, something like a phase change in a larger, ongoing system. These ideas are still speculative, and they require strong evidence before they can be taken seriously. But the fact that they are being discussed at all shows how significant these new observations are. What makes this moment so important is not just the data itself, but what it represents. For the first time, we are directly observing a period of cosmic history that was previously hidden from us. And instead of confirming everything we expected, it's revealing new layers of complexity. This is how science moves forward, not by confirming what we already know, but by challenging it. And right now, the universe is doing exactly that. It's showing us that even our most trusted models may only be part of a much larger story. What makes these discoveries so powerful is not just what they show, but what they question. The James Webb Space Telescope isn't just revealing distant galaxies, it's exposing gaps in our understanding of how the universe evolved. And that's what makes this moment so exciting. Because every time we look deeper, the universe doesn't just give us answers, it gives us better questions. So here's the real one. Are we seeing the true beginning of everything, or just a small chapter of a much bigger cosmic story? Drop your thoughts in the comments. I'm genuinely curious. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries. Your support truly makes a difference and helps this channel grow. Thank you for watching, and see you next time.